We're going to start our discussion about techniques of integration by going through a review of the U-substitution technique. So we're going to kind of tie all of those U-substitution techniques and those formulas and rules that we learned last fall. This is just going to be a quick review of them. We'll work some examples, and then we'll do some homework problems, and then we'll learn new techniques of integration in the following lessons. So, the effective use of the method of substitution depends on the ready availability of a list of known integrals. We know all these already. This is just a review. This short list should have already been memorized. You should know all of these already, but here's just kind of sort of a review since it's been a while since we worked with them. If we are finding the antiderivative of a real number value k is some real number value, then the antiderivative of that is k times the variable which with respect to we are integrating. Here we're integrating with respect to u, so this is just k times u. We have the power rule for integrals. Here's the power rule for integrals. This is the top part of it here. We have two cases when we have u raised to a power r. If r is any other value except -1, okay, for all other values except r equals -1, the power rule is 1 over r plus 1 times u to the r plus 1. For the case where r is -1, we have the integral of u to the -1 du. We learned that's the integral 1 over u du. The antiderivative there is the natural log of u. We don't worry about the absolute value on the expression here of our natural log unless we're dealing with a definite integral that has us, entering negative values, because the natural log function doesn't have any negative value input values. So we usually just write the natural log of our expression in parentheses, but remember it actually is absolute value, so that if we're putting in negative values, instead of saying that's undefined, it's equivalent to the natural log of the absolute value of those negative input values. This one's easy since e to the u is its own derivative, e to the u is its own antiderivative. Under u substitution, we may be off by a constant. That's true for these others as well. Here's the general exponential function, which is the same as e to the u, except we are dividing by the natural log of a, or 1 over the natural log of a times a to the u. It's the natural log of the base, right? Not the expression, the natural log of the base. This is a real number. A is some real number, and then u is our expression in x. What did we take the derivative of to get positive sign for the answer? Well, that was negative cosine. What did we take the derivative of to get positive cosine for the answer? Well, that was positive sine. So knowing the derivative rules and then applying them backwards help us with these two integral rules. There are 4 additional ones. Since we know that the derivative of tangent is secant squared, then we should know the antiderivative of secant squared is tangent. We don't necessarily know or have memorized that the integral of tangent of u du is the negative natural log of cosine of u, but what we do know is that the sine of u over the cosine of u du is a u substitution. Here I'm going to call it a v substitution. We'll say v is the cosine of u. It's what's being operated on. It's how it got down there in the denominator of a fraction. So the derivative of that is negative sine of v dv. And so I can rewrite this now as the integral of 1 over v dv, and I'm off by a negative. So do you see the natural log going to show up there? So that's negative natural log of the absolute value of v plus c. We said v was the cosine of u. So we do wind up with the negative natural log of the cosine of u plus c. So the reason I haven't had you memorize this as the antiderivative is because under u substitution we can find it fairly easily. All right, and now this was the sine inverse. We look for the form of a real number squared minus some expression in a variable squared, right? And under a square root sign in the denominator of a fraction, that points us to sine inverse. Remember, u is the expression in the variable. It's the variable expression. And a is the real number value. All right? And for tan inverse, we have to remember that it's 1 over a times the tan inverse of u over a. There is no root sign in the denominator, and it is the sum of the squares of the real number value and the expression in our variable value. All right, so all of those we've worked with, all of those that we know those. So let's just do a review. Let's work some examples here. This is a u substitution. The method of substitution we call u substitution. If something is being operated on, then we always try u substitution. We pick that thing that's being operated on as u. We ignore the original integrand. We find our du. Then we come back to our integrand and we try to completely rewrite it in terms of u and du only, so that if we were to back substitute our choices here, we said that u was x plus 2. We said that when that's u to the 5th, we said that du was dx. So that if we back substituted our choices, we should wind up where we started. That tells us we have made a good u substitution choice and that this is equivalent to the original integral. And then we can just apply whatever of those last rules that we talked about to find the antiderivative of that function. And then the last step is to substitute back in for what our choice for u was. And we're guaranteed this will be the antiderivative of the original function that we were given. The same thing here. What's being operated on is what was put into the square root function, so 4x minus 1. The derivative of my choice for u is 4 times dx. Remember, we're finding the derivative. This is where the differentials showed up. We're finding the derivative of u with respect to x, and then we're multiplying both sides by dx, and this gives us the differential, so we know what du is equal to. So we can equivalently rewrite this integral in terms of u. That's the square root of u. If I write du, though, I have a problem. This 4 is not in the original integral. Du is 4 dx's. I only need 1 dx. So I'm going to take 1/4 of du, and we're used to now popping that constant out front because we realize all of this is multiplication. So we have 1/4 the integral of u to the 1/2 du. We find the antiderivative. I pop my 1/4 out front. That's 1 over n plus 1 u to the n plus 1 plus c, because we're dealing with the indefinite integral. So we can clean this up. This is 1/4. 1 over 3/2 is 2/3. U to the 3/2 plus c. So we could clean this up. That's going to clean up to 1/2. So the answer here is 1/6 u to the 3/2 plus c. And remember, the final step is always to take u home. U brought, Y-O-U, brought u, the letter u, to the party. You have to take it back home. That's the last step in u substitution. And we're guaranteed that this is the antiderivative function, meaning if I took the derivative of this function, this is what I would get for the answer. All right, a couple more examples. What's being operated on here is the sine function. So I'm going to pick that as u. That means du has to be positive cosine of x dx. Completely rewriting that original integral in terms of u and du. U is the sine of x. It's raised to the power of 4. That's u to the 4th. And du is cosine of dx. So find the antiderivative, u to the 5th plus c, and take u home. You brought u to the party, you have to take u back home. All right, so fairly straightforward. Here, this is a little bit different. I don't really see, clearly what's being operated on is what's in the denominator of this fraction. The only way it got down there was to be put into a function machine. So I pick that as u. I find du, which is 2x minus 6 dx. But my issue is all that I've got outside of 1 over this choice for u is 7 dx, and that definitely does not equal 7 dx or any portion of it. Here's my biggest problem. I can't be off by a variable. I can be off by a constant. We saw that. Let's see here. I can be off by a constant. That's not an issue. I know how to fix that. I can't be off by a variable. If a variable shows up in my choice for du and it's not up here, right, then this is not a straightforward u substitution. This was not a good choice for u. So now I have to kind of drop back and punt and maybe mess with things a little bit. I'm going to pop that 7 out front. I have 1 over this fraction. I'm just going to put my dx there. So now I'm going to ask myself, what can I do with this expression to help me find the antiderivative? Is there a way for me to rewrite it? Is there anything that I can do here? Well, I don't know if you remember or not, but we did say that we can try to complete the square on this portion of a quadratic equation, and we can borrow some of the value from that 25 that we need. Here we would take half of this, which is -3, and we would square it. That would be 9. And that's going to give us that repeated factor. Remember, that repeated factor is going to help us here. And so I've borrowed 9 of those 25. That leaves me 16. So that's 4 squared. So let's rewrite this one more time. That's 7 times the integral of 1 over, I'm going to write 4 here, and maybe you kind of see what is happening. This is not as straightforward as our other u substitutions. We have to kind of mess around with it a little bit and see what's going on. But do you see 1 over a squared plus u squared here? I definitely see that. So this is telling me that my antiderivative is going to involve tan inverse. And so I need to choose u, that's x minus 3. I need to choose du, the derivative of x is 1 with respect to x. And I need to identify that I recognize a equals 4. Now I still have this 7 out front. I'm just going to copy it down and then go about rewriting things in terms of u and du and all that. So now I have the integral of 1 over, I still have my 4 squared, but now I have u squared du. So if I was to back substitute this in for u and this in for du, is this equivalent to that? Are those two things equivalent? Because if they are, then I can go about finding the antiderivative of this function. And they definitely are. I'm going to pop my 7 out front. I have 1 over a times the tangent inverse of u over a. And there I have found my antiderivative function. And I have back substituted. As a matter of fact, let's really quickly, that needs to be in terms of u. That should be u over 4. And then my last step here really quickly is to back substitute and take u home. So there would be all of the steps that I would need. I'll stop here. We have another couple of examples and then we'll move on.